All right, we might kick off. So good morning, everyone. I think it's still morning. Yes, good morning. Welcome everyone to the last of our 2025 CEBRA research webinars, or CEBRAnars as we have grown to know them. My name is Lisa Skorowski. I'm Assistant Director of the Research and Innovation section within the Biosecurity Strategy and Reform Division here at DAF. Firstly, I wish to acknowledge the Turrbal and Yagara people as traditional custodians of the land that I stand on today. I wish to acknowledge and respect their continuing culture and the contribution they make to the life of this city and region. I extend that recognition to the traditional custodians of all other lands on which our staff and participants are gathered today, and to all Aboriginal and Torres Strait Islander peoples attending today's webinar. As always, we have attendees from many different places, so feel free to pop in the chat the lands from which you are joining us from today. Before we begin, can I ask that everyone except our presenter ensure microphones are on mute and cameras are off. Today's session will be recorded and available for those unable to attend. There will be an opportunity to ask questions after the presentation by either using the hand up gesture or posting a question in the chat panel. For the newcomers, the Centre of Excellence for Biosecurity Risk Analysis, or CEBRA, is a long-standing biosecurity research initiative hosted by the University of Melbourne. With a new 4-year agreement now underway, CEBRA will continue to provide the Australian and New Zealand governments with expert biosecurity risk analysis and advice that helps inform a range of biosecurity risk management activities. Today, we will hear from Dr. Edith Arndt, who will provide insight into an innovative resource allocation tool developed by CEBRA. Edith will walk us through the approach behind the tool, demonstrating its application in the C container pathway and how it can help decision makers optimise resource allocation and strategic planning in border security. Edith is an alpine ecologist and senior research fellow at CEBRA. Her work focuses on improving biosecurity through research in border resource allocation, community engagement for general surveillance, evaluation frameworks, impact evaluation, resilience thinking, and marine biofouling. So please join me in welcoming Edith.
Thank you so much for the introduction, and good morning to everyone who is joining us today for the very last CEBRAnar for this year. So I will now share my screen. So hopefully you can all see my screen now.
Yes.
I just need to get rid of this window here. I'll just park it down here. Okay, so before I go into the presentation, I would like to acknowledge the traditional owners of the land on which I talk to you today, the Wurundjeri, Woiwurrung and Bunurong peoples, and I pay my respect to the elders past, present and emerging. And I acknowledge the importance of Indigenous knowledge in the Academy. So the outcomes of this project are the work of many. So I'm the lucky one who can talk about this project to you today. But I'd like to point out the contribution that the various people have made to this project. And we have got Dr. Arndt here. He was the project manager in the first year of the project. So he developed the project idea with our DAF colleagues, and he got this project off the ground. And after about a year, Aaron resigned, and that's when I took over the coordination of the project. We have Dr. John Baumgartner here as last in the list, but as it is custom in the natural sciences, it just points out his central role in this project as the chief programmer. So he wrote all of the R code for this project, and he made sure to convert our great ideas into an end product. Associate Professor Anke Hania brought in her expertise with Bayesian networks and many other things to this project. Professor Andrew Robinson supported this project with his guidance and advice, especially around the handover from Aaron to myself. Doctors Chris Baker and Tao Li did a wonderful work on modeling the second pathway for this project. And Dr. David Rolls supported us with processing the data that we received. So at the end of the presentation, you will briefly hear from Professor Tom Kompes, because I've asked him to fill us in on the work that he's currently involved in that relates to this project. Okay, so this project today is about a simple resource allocation tool for optimizing border measures. And this slide is to remind us of the complexity of the border biosecurity space. We have got many entry pathways that can allow exotic pests and diseases to enter into Australia. So what are entry pathways? Some examples: that can be commercial cargo, that can be international passengers, international mail, shipping containers, and also conveyances. And each of these pathways poses the risk of introducing biosecurity risk material. That's why we have a mix of risk controls for each of the pathways. And the number and the sequence of these pathways depends on the pathway. And risk controls, for example, are document assessments and then inspections and treatments. So when we make resource allocation decisions in this context, we have to consider different factors, including the type of risk controls and how effective they are. But there are also dependencies in the system, dependencies through investing and doing resource allocation, because if we invest more into one risk controls, there will be less to invest elsewhere. We've got dependencies through inspections. We have inspections that target the same species, for example, and we are faced with multiple threats. So a range of species can affect horticultural species, for example, in Australia. It's not just one pest or disease that arrives that just targets one horticultural industry. So multiple species can affect multiple assets. So it's a many-to-many relationship. And then, of course, we have got the leakage rate. This is the number of biosecurity risk material that crosses our borders undetected every year. And obviously, we want to keep this leakage rate as low as possible. So the question now in this context is, how do decision makers best allocate their border biosecurity resources across interventions to minimize biosecurity risk, to keep this leakage rate low? So what's the investment strategy? So where we have complex decisions to make, we can use models to help us with the decision making. And that was the project objective. So the objective was to help DEV reduce the biosecurity risk of imports arriving via different entry pathways by developing a proof of concept resource allocation tool. So the emphasis here is on proof of concept. And in the early stages of the project, we worked out what key functionality end users would like to see in a resource allocation tool. So we held a series of user requirement workshops, and we ended up with 3 key functionalities that we built into the tool. So the first one is the tool should allow users to minimize the cost of achieving ALOP, so to select the best combination of risk controls to achieve an appropriate level of protection for Australia. So if there is a fixed budget and we have got 2 risk controls to invest in, the tool should allow to optimize investment and maximize the benefit, which is risk reduction. And the third functionality is if we invest into multiple risk controls across multiple pathways, we want to again achieve maximum benefit, maximum value from our investment, but minimize the costs for that. So in this project, we were lucky that we didn't start from scratch. We already had something that we could build on. And that something is actually a substantial piece of work that was completed by CEBRA in 2020. It's a consequence model that can estimate damages, and we called it the value model. So a few members in the audience might have heard about the value model, but I'll just give a brief introduction to this model again. So the value model is a spatio-temporal simulation model that was initially developed to estimate the net present value of the biosecurity system in Australia. So the model can estimate damages by modeling the arrival, establishment, spread, and impact of 40 functional groups, and then estimating the impact of these 40 functional groups on 16 different asset classes. And we have got those asset classes here on the right. They range from agriculture to forestry, infrastructure, through to water, for example, and tourism. So the model estimates damages per pixel. So if an asset and an invasive species are both present in one pixel, then the value model multiplies the percentage yield reduction caused by that species with the asset value present in the pixel. The model does not allow double counting of damages. So if two simulated pests affect the same point in the landscape, the model takes that into account and adjusts the damages accordingly. Okay, so this is our research approach for this project. We're looking here at the back end of the tool. And so we were thinking, if you want to optimize resource allocation at the border, you first have to understand the risk controls on a particular entry pathway. So what controls are there, how many, and how effective are they? So we developed two pathway models in this project. One is the sea containers and containerized cargo pathway, which I will refer to as the container pathway. And the second one is the cut flowers and foliage pathway. So in today's presentation, I will focus on the container pathway. So the purpose of developing a pathway model was to simulate the interactions of the sea containers with the risk controls on that pathway that are implemented already. And as we can see here on this diagram, the output of the pathway model is the leakage rate, which is basically the arrival rate, so something has arrived. And this then gets translated into an establishment rate. Because the input into the value model, our consequences model that can estimate damages, is or are establishment rates. So the value model usually uses establishment rates that were estimated through the department's CEBRA model, the risk return risk allocation model. But in our case, because we have got our pathway models, the input into the value model is then the establishment rate that we have worked out through our pathway models. So the leakage rate that is the output of our pathway models is influenced by the decisions, the management decisions that we have made on this pathway. So if we have dialed risk controls up or down, we should see a response in the leakage rate. And that leakage rate will travel through to the value model. And the value model then can quantify the extent of that response as a change in damages. So we should be able to see a change in damages in dollar values based on the management decisions that we have made here on the pathway. So this approach will allow us to see the consequences of decisions in a safe testbed environment before we are implementing anything. So the tool in the back end links these two things together, the pathway model and then the value model. So this shows an overview of the methodology that we used to develop our pathways in this project. So we first started with a conceptual model, which describes what happens on the container pathway. So how containers interact with the implemented risk controls based on the container attributes. The second step was to develop a model structure that's based on the conceptual diagram. And we undertook a desktop review on that, showed us that the best way how to do this is to use the qualitative part of Bayesian networks to model the relationships between variables. So while we were still undertaking step one, we put out a data request to the department and we had some data delivered. And so we could then parameterize our model structure with actual data. And then we have a simulation model. We developed the simulation model in step 3. So the simulation model simulates the interactions of the containers with the biosecurity risk controls, and then gives us an estimate of the leakage rate. So that's the output of the simulation model. So in the next 3 slides, I will talk about these 3 steps in a little bit more detail. So here we are looking at the conceptual diagram of the container pathway. And so we developed that by first reading some material that was provided to us by the department, so some work instructions and policy documents. And then we had some follow-up consultations with experts in the department to make sure that our initial drawing of the diagram actually makes sense. And we worked out that the answers to 4 questions determine which risk controls most of the containers will interact with. And these 4 questions are, you can see them here on the right. So are the containers coming from a country that's on the country of action list? Have the containers been treated under the sea container hygiene system or not? Do the containers have a rural destination or a metro destination? And are the containers empty or full? So you can see the container pathway has got 2 pathways in it, a high-risk pathway here on the left, and then a low-risk pathway here on the right. So the high-risk pathway is associated with containers that are coming from high-risk countries, so countries that are on the country of action list. And these containers will undergo a 6-sided external CAL inspection if they have not been treated under the sea container hygiene system. So if the containers from CAL countries have received treatment through the sea container hygiene system, they can receive a reduced inspection rate. So if the containers are full, then depending on where they are going, if they have got a rural destination or not, and what the type of goods are, they may undergo another external inspection, or they might be unpacked at an approved arrangement. So this conceptual diagram is actually quite exciting because it's the first time that someone has actually visualized what's happening on the container pathway and depicted the interactions that are taking place on the container pathway. So the next step was then to translate this conceptual diagram into a model structure. And here we use the graphical advantages of Bayesian networks for structuring the model. So the use of Bayesian networks allows to model complex relationships, and you can also integrate data from different sources. And here we can see the qualitative part of the Bayesian network. It consists of a set of variables. They are represented as nodes, as we can see here. And then there is arcs connecting these nodes. But the arcs do not represent a flow, but rather dependency and causality between the variables. So in our model structure, we had 4 top-level correlated attributes that influence which interventions are undertaken on the pathway. And you might see that they represent the 4 questions that are showed on the previous slide. So rural destination, type of goods, CAL country, and then the C container hygiene system. So in the middle, we have got our different types of interventions, internal and external inspections, the different types of those inspections. And down here, we have got the approach rate represented in the model. This is the true contamination, but we have not observed that. As we can see, the true contamination, the approach rate, is influenced by all of these top-level correlated attributes. So there's an arc going from all of the nodes up here going into the approach rate node. So because we don't know the approach rate, we have to infer it and estimate it from the observed detection rate and assumed inspection sensitivity. So the inspection sensitivity is the probability of correctly labeling a contaminated container as being contaminated. So detected contamination can be treated, and depending on both the effectiveness of the treatment and then on the outputs of our internal and external inspections, we get the leakage rate at the end, the leaked contamination. So this is our model output. We've got two parts, internal and external leakage rate. Okay, so once we had this model structure, we could parameterize the model with data delivered by the department. So we were working with import management and border inspection data from the S-Cargo and the AIMS databases. And the type of information that was included in these data sets was the country of origin, the tariff code, the type of goods, some sort of description of the goods. And then we also had data from the cargo compliance verification system. And yeah, as I said before, some inspection data, some interception data. So we had to restrict the data to the period of 2018, the fourth quarter, to 2022, the third quarter, because sometime in 2018, the border biosecurity system in relation to containerized goods underwent some significant changes, and we felt the earlier data would then not be representative of the current system. We also undertook some data cleaning, so we removed any containers that did not have an AIMS direction or an AIMS entry or a direction or a final direction. And in the end, we worked with about 2 million containers in this project. And we created conditional probability tables for most of the nodes. And we did that by examining the data that we received, and we looked at how often an outcome would occur under different circumstances. And then we recorded those probabilities in a structured table, in a conditional probability table. So you can see an example of a conditional probability table here on the right. We have got, so one of the nodes in the model is the node for external inspections, the CAL six-sided inspections, and we can see that this node has got two parent nodes, CAL country and the C container hygiene system. So the CAL country node has got two different states. We can see that here in the table. So it's either true or false. So either the containers are coming from a CAL country or they're not. And the C container hygiene system has got how many? 5 different states. So one of them is whether the containers did go through a facility or not, and then we've got the different inspection rates here, ranging from 5 to 100%. And the CAL six-sided node has got 2 states. So either there was a six-sided CAL inspection undertaken or not. So it's either true or false. So here we can see the probabilities of these different circumstances, whether they have led to a six-sided inspection being undertaken or not. So, for example, there were containers that were coming from a CAL country, so the state here was true. They underwent, or they had an inspection regime of 20%. And then this table gives us how, like, what's the likelihood, what does the likelihood look like for the combination of these different states here. So this likelihood might be like 30% or 70%, and then here we would have the opposite number that makes up to like 100%. And just wanted to point out these probabilities, they vary across the table, so they're not all the same. It depends on the combination of states, what their value is. So the objective of the project was to develop a resource allocation tool, but the simulation model that sort of that this tool is based on in itself is very useful, because with the fully parameterized simulation model, you can answer questions that you may have about your pathway. And these questions can include changes to the top-level correlated attributes, like the CAL countries, for example. So we had a range of counterfactual examples that we looked at in the project, but I've just picked out one as an example. So these what-if scenarios. One of the what-if scenarios was what would happen to the leakage rate if we increase the proportion of countries on the CAL. So we've got more countries on the country of action list. So we can see here on the y-axis the leakage rate, and on the x-axis the proportion of countries that are on the CAL. And we can see that the leakage rate increases the more countries are on the country of action list. And this is not unexpected, because if we have got more containers coming in from high-risk countries, they will have more external contamination on them, and more of that contamination can leak through the risk controls. So we also undertook some sensitivity analysis. So we this is also an example here. We changed the values of two parameters in our model to see how that would affect the leakage rate. And in this case, we changed the effectiveness of the inspections and the treatments. So we varied the inspections from 70% effectiveness to 100% effectiveness, and the treatment effectiveness was varied between 50 and 100%. So with increasing inspection effectiveness, we can see that the leakage rate decreased, which is not surprising, because if we are getting better at inspections, we are more likely to pick up any contamination, and less biosecurity risk material would leak through that risk control. And the same story with treatment effectiveness. The better we are with removing contamination from the containers, the less material will leak through. So the leakage rate decreases as well. Okay, so finally, this is about the front end of the tool. So the user-facing front end of the tool is an R Shiny web application, and it integrates our two pathway models with the value model. So the resource allocation tool has got a user interface with different tabs. There's a settings tab and an analysis tab, where you can compare different resource allocation scenarios. So the costs are currently not implemented in this proof of concept version, because at the time when we developed this tool, it was unclear how cost scales with inspection effort. But the costs of risk controls can be compared to the benefits that the tool works out, the avoided damages. So after running some different investment scenarios, so you can compare costs with benefit outside of the tool. So this is what the settings tab looks like. This is where users can define some inputs to the simulation. So up over here, we can say that we can see that they can choose what the spatial extent should be. There's a demo spatial extent, and the full extent, which is the Australian continent. And then users can select the duration of the simulation and the number of iterations. And down here, they can enter the number of containers that are arriving per year. So this is the number of containers that are referred to AIMS through the ICS, the Integrated Cargo System. And then users can also enter values for global inspection effectiveness. So at the moment, this is set to 90%, so 0.9. And again, the inspection effectiveness or sensitivity is the probability of correctly labeling contaminated containers as being contaminated. And here on the right, you can enter and specify alternative scenarios for inspection effectiveness. And so the inspection effectiveness can range from 0 to 1. So either a 0% chance of detecting contamination or a 100% chance. And this is the place in the tool where you can change resource allocation to risk controls. So you do this by varying inspection effectiveness of individual inspection methods. So here we can see the different inspection methods that are implemented on the containers pathway and the ones for the cut flowers pathway. So the assumption is that the more we invest into an inspection method, it will increase its inspection effectiveness. So there's a link between effectiveness and investment here. And on the second tab, this is where users can select the species that they would like to simulate the arrival establishment spread and impact for. And ideally, this would be the species that have been detected on the pathway before. So the species that have some sort of significance for that pathway. So for the container pathway, it's the giant African snail, the capra beetle, BMSB would be one, or the spongy moth. And then users can select the pathways that they want to include in the analysis. That can be 1 or 2 pathways at the moment. So we have got the container pathway selected here. And then they select the controls that they would like to be included in the analysis. And these would be the controls that you have specified your inspection effectiveness for. So in this example, it shows the specified inspection effectiveness for the external, that's internal. This one up here, the external rule tailgate inspection, that's on the low risk pathway. And that's what's selected in this example here. You may notice there's also a link or an interface to the value model, the standard value model, but I'm not going to talk about this today. It basically allows you to run simulations with the biosecurity on and off. And so this is how the results of a run are presented in the tool. So what the tool does, it compares the different investment scenarios to a status quo, and the status quo is always the first state that's specified in the settings tab. So which is 0% effectiveness of the inspections. So all the other investment scenarios are compared to that very first one here, the 0% investment scenario. And so the tool gives you average damage, a standard error for the mean, median damage, then the benefit, and a standard error for the benefit as well. And we can see here that with increasing investment, so a change in the effectiveness, that the damages decrease and the benefit increases. So you can run these different resource allocation scenarios and use more than one risk control, and also you can do this across 2 pathways. We've just shown you a simple version of what the tool can do for today. And so this brings me to the end of my presentation. So in wrapping up, I'd like to point out this is a proof of concept at the moment, which has not been implemented, but this modeling approach or this idea has got a lot of potential and it is flexible, which means we can include more pathways if we wish to do so. And we can also include the costs. So the tool is flexible enough, so in the future you can compare benefits to costs all in the same place, all in the tool. And the development of the simulation model can be generalized, so which means if we decide to add more pathways to the tool, we can go through these general steps, what I've shown you in the presentation. So first you start with a conceptual model, then you develop a model structure, and then you parameterize with data. And some of the top level correlated attributes would be the same across pathways. So for example, the source country, the type of goods. And there's some other things that will always kind of be the same, like the reasoning will stay the same. That's the observed contamination rate will always be a function of the true contamination rate, the approach rate, and the detection capability, which is the inspection sensitivity. So things that can vary or will vary if you add other pathways, of course, is the type of interventions. So there are a few potential extensions that you could do to this piece of work, and I'm starting with the points 2 and 3 here. So at the moment, the value model treats container volumes and host susceptibility as static, so things that do not change over time. But like a 50-year simulation period is a long time, so it's unlikely that these things will not change. So future work could then look into or consider changes in container volumes between countries over time, and also consider the changes in the susceptibility of the landscape over time due to climate change. And I'd just like to highlight that CEBRA Project 21B has done some work in that space, like with climate change and trade volumes. They simulated climate-induced changes in global trade and then predicted how that would influence contamination rates for imports from different trading partners. And at this point, I would like to hand you over to Tom, who can talk a little bit about another potential extension, which is to include post-border management, like, for example, eradication, and see how that might change estimated damages.
Yeah, thank you, Edith. Yeah, I want to talk about two extensions that CEBRA is working on. But before I do that, let me say this: I wasn't directly involved in the project that Edith just nicely described, but I love it. As an economist, I love this work because it's focusing on rates of return. You know, if we spend additional money for a biosecurity measure, what's the extra benefit? That's innovative. That's very important, and indeed very important for decision making. The two extensions are the following. Edith's already mentioned the 21B sort of work in terms of changes in pest pathways as a result of global warming, or as a result of Trump tariffs, or as a result of any change in trade agreements. That's there, and it's already online in the CEBRA web space. But the other two extensions that I want to highlight first is what we've done. We've taken this work, the value model, the CEBRA DAF value model, plus the work that Edith has described, and constructed a similar sort of platform for Biosecurity New Zealand, working very closely with Dr. Mike Ormsby. Now that model, that value model for New Zealand, includes both pre-border, border, and post-border layers, unlike the current DAF model, CEBRA DAF model. So it allows you to sort of think about the entire spectrum for biosecurity measures. But more than that, or in addition to that, it also includes something called a value max model, which asks the question: if you spend dollars pre-border, border, post-border, where's the best rate of return across a number of different pests and a number of different asset layers? So it's taking the DAF CEBRA value model and extending it across layers, across pests, and asking the question, what's the best rate of return? So hopefully I'll present, or some of us at CEBRA will present that work next year in a CEBRAnar, and see if we can get Mike Ormsby along as well. But that's quite cool. It's telling people in New Zealand that, look, there could be a big return, a big marginal return on pre-border measures compared to post-border, for example. And we'll spell that out when we do the CEBRAnar. The second sort of extension is our current project with DAF called 25C, which is going back to the value model that was developed initially that Edith talked about, revising the establishment rates, arrival and establishment rates, doing much more work on the asset layers, and indeed, potentially at some point asking the question, if we include pre-border and post-border material, what again is the best rate of return? What's the value max? Where should the money go, in effect, to generate the best benefit? What's also nice about that project that we've just started is that we're going back to the original value model code, making it much more usable, and indeed much more usable in-house in DAF, so that they can run it in their own setting using their own platform, and ask the question, well, much like Edith was asking, well, if there's a change in the establishment rate for some particular pest along the pathway, what's the impact in terms of damages? So all of that's really got us very excited, because we're sort of tit for tat here with New Zealand, using the value model in Australia, extending it to New Zealand, and then using the New Zealand model and bringing it back to Australia for the CEBRA DAF value model extensions. So I'll keep you up to date on that, and indeed CEBRA will as well. But that's what we're planning going forward, and hopefully we'll be able to give again, as I mentioned, a CEBRAnar next year on this material. But congratulations to Edith. I think that was a great presentation. Edith, I'm going to turn it back to you just to say a thank you and wrap up.
Okay, thank you so much, Tom, for giving us some insight in what else is happening at CEBRA at the moment. And I just wanted to wrap up with a thank you slide. So we have worked with a lot of different people in this project in the department, and we are very thankful to each one of them. It was a great pleasure to work with each one of them, and we wanted to thank you for their strong support and interest in the project throughout the years. Okay, and with this, I end here and hand over to Lisa.
Thank you, Edith and Tom, for your insights today. I am particularly excited about having a CEBRAnar next year to discuss the value max model, because I think it's fantastic work. It's really keeping things relevant as well, and keeping, a suite of tools that can actually help us with our decision making here in the department, and then also too for New Zealand. So it's very important work, and I'm actually really looking forward to having that work presented next year. But again, thank you for the insights. Now I'll just check to see if anyone's got any questions before we finish up today. So yeah, either pop your hand up, put them in the chat, whatever floats your boat, really. So I'll give a few minutes for people to come forward if they have anything. Andrew, come on down.
So, resistant as I am in my crusty old age to these newfangled economic ideas, I was delighted to see the prospect of thinking about pre-border and the value of pre-border measures being introduced to the conversation, because I've been working with DAF and MPI to look at a particular program called the Sea Container Hygiene Scheme that specifies that containers have to be cleaned when they pass through certain ports before they come to Australia and New Zealand, and that if they arrive under the scheme, then they get reduced intervention on arrival. And it would be, given that there is inspection data available on these containers, it would be intriguing to to determine what the value is of the scheme to Australia and New Zealand.
Yeah, that's a really good point, Andrew. Thank you. I'll bring that up with Mike Ormsby in New Zealand as well and see if we can tie that down. I think that'd be a really cool project.
I think there was a question from Mike, if I'm correct.
Yep. It's got, have you solved the question of how cost scales with risk management efficacy?
No, not yet. So we thought about including dummy cost data instead of some real cost data for the risk controls. But in the end, we didn't. But I think that could be something to work on to kind of really get an understanding about how much these risk controls cost and how that scales with inspection effort. Yeah, so something to work on in the future to then really bring it into one place, which would be quite neat.
Anyone else got any questions? I feel like an auctioneer. It's like going once, going twice. Andrew again.
Yeah, I've got another one. Sorry. So, Edith, you showed a really interesting slide, which piqued my curiosity, that looked at the sort of interplay between treatment effectiveness and inspection effectiveness.
Yes.
And from my casual glance, it looked as though inspection effectiveness was more important to getting low leakage than treatment effectiveness, which does make sense. But I also wonder, were all of the treated containers subsequently inspected, or were only a subset subsequently inspected?
That's a good question. There was a reinspection. I'm not quite sure if it was all of them. I suspect treated all of them were reinspected, but maybe Anka or John have got some insight. This is kind of a while ago. We have got a reinspection sort of box on our conceptual diagram. But that's a very good question. I think we assumed 100% effectiveness of the treatment for the modeling exercise.
Sure. Yeah. Okay. So that might play out a little differently if the regulator were to decide that rather than inspect all of the containers post-treatment, they would inspect a sample of the containers post-treatment. Because otherwise, the message that I got is that inspection, let's call it verity or quality, is more important than treatment quality. And that's true if inspection's the last thing you do, but only if you're inspecting everything you treat, which operationally might not be true.
Yeah. Good point. Thank you, Andrew.
Michael popped another question in the chat. Are you looking to include benefits other than damage avoided, example, market access?
We haven't done this for the proof of concept, but I think for any additional or potential future work, yeah, definitely that would be something to include. And maybe Tom has got an update on that.
Yeah, so it's considered in the New Zealand model for sure. Looking at pre-border measures based upon Mike's work in particular. Yeah, it's something I'll talk about in the CEBRAnar and get Mike involved as well.
Yeah,
because in many cases the major damage is indeed from loss in trade rather than direct damages to individual asset layers. Trade impacts can be huge. I mean, FMD is a classic example. Yeah, the trade impact for Australia would be quite large.
Yeah, this was to demonstrate that this can be done. So yeah, definitely the modeling approach, it's all flexible to build on what we already have. Yeah, definitely.
That's right. Exactly right.
We've got another question that's come through. Do you have recommendations how to assess inspection or treatment overall control effectiveness in a systemic approach across DAF?
Do you want to take that, Tom? Or
Well, that's kind of what the work is doing. It still needs further refinement, but that's exactly what it's trying to do. Yeah, Edith, do you think? I think so.
yeah, so we worked with an assumed inspection effectiveness. Yeah, and we
Yeah.
it would be good to get some actual observed inspection effectiveness data on the different types of inspections.
Yeah, so there is a project that we're working on called 25D that's looking at pre-border measures. Siam wheat from Thailand, for example, where we could start to flesh out some of this sort of impact, this sort of analysis more deeply. So I think, eventually all of these things that CEBRA is doing is going to tie together. We have pre-border projects, we have a value project, we have the project that Edith described, we have all the fine work that the team is doing, including Andrew and what he's mentioned today. It all sort of comes together in the end. It's really quite nice. So we'll use all this information and indeed try and tie it together for DAF.
Yeah.
Excellent. So I think there's a bit of chat going on in the chat about the treatment versus reinspection details there. So hopefully that helps, pull that together. But if no one else has any questions or is willing to pop their hand up, we'll wrap up for today and for the year. But thank you for today. Thank you for joining us. Thank you to Edith, Tom, Andrew for sharing his insight. And we've obviously recorded today, so it will be available on CEBRA's YouTube channel shortly. But head on over there because all of the other CEBRAnars we've done, all the recordings are there as well. So feel free to have a look. And we hope that you have enjoyed this year's series and will be here with us next year when we kick off in 2026. But you can also follow us on Humanitics. Then that way, whatever information comes out early on in the piece, you're the first to hear. So, but again, thank you for joining. Thank you for a great year. And everyone have a fantastic day.
Thank you, Lisa. Thank you very much. And thanks to everyone for joining in today.